Welcome to the CFE Media and Technology education session. Back to basics, motor efficiency, and the advantages of adjustable speed drives to achieve energy savings. I'm your moderator, Mark T. Hosky, with CFE Media and Technology. In keeping with our CEP policy, please take some time to read the quality assurance slide. This session is designed for technicians and engineers who want to understand best practices to learn about energy savings through motor efficiencies, drive attributes including programming by understanding laws, standards, and designs of motor drive systems. Expert presenters will look at standards, technologies, motor and drive sizing, load laws, and definitions with examples. Software can help estimate motor drive energy savings with metrics that matter for specifying motors and drives. Here is a list of learning objectives for today's session. We'll cover these in the presentation. Additional resources for the presentation can be viewed and downloaded on the left side of the screen below the session's agenda. For a seamless online experience, here are some tips. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. If you'd like to take notes within the session, click on the left panel labeled Notes to do so. This session is available on demand if you need to come back at any time. Please remember that the session will be made live at 2 p.m. Central, 3 p.m. Eastern, with a Q&A starting approximately at 2:45 p.m. Central and 3:45 p.m. Eastern, or immediately after the presentation ends if it runs a little longer than 45 minutes. Industry experts will answer the viewer questions live, and those answers will be archived with the session. You can see the Q&A details in the Meetings tab on the left side of the screen. Here is some information about obtaining an approved PDH for today's session. Today's speakers are Glenn Klein, Senior Technical Specialist, Low Voltage Motors, Motors and Drive Division, and Joshua Jagnanan, Senior Application Engineer, Low Voltage Adjustable Speed Drives, Motor and Drives Division, both with Toshiba International Corporation. I'm your moderator, Mark T. Hosky, Content Manager, CFE Media and Technology. Next, a little more about each speaker. Glenn Klein has been with Toshiba for over 40 years. Glenn started working part-time with Toshiba while attending Texas A&M University and has grown with Toshiba, having served in many roles over the years. For the last 20 years, Glenn has served as an application specialist for the Low Voltage Motor Group. He has over 20 years experience as a training instructor for Toshiba. Early in his career, Glenn held a variety of roles at Toshiba, such as forklift operator, customer service representative, customer service manager, export control office, and application specialist for power apparatus and components products. Joshua Jagnanan has served as an application engineer in the Low Voltage Application Speed Drives product group for over 7 years. On a daily basis, Josh interfaces with customers to provide support for drive programming, commissioning, troubleshooting, and technical training. He has a unique experience of supporting numerous motor and drive application needs in a variety of industries such as HVAC, oil and gas, water, wastewater, aggregate, cement, agriculture, power generation, and more. Josh attended the University of Texas at Austin, where he earned a Bachelor of Science in Electrical Engineering. Glenn and Joshua, thanks for joining us. Please go ahead with your presentation.
Yeah, thank you, Mark. This is Glenn Klein, and I'm going to be going through the first portion here, talking about motor efficiency, and then my coworker Josh will talk a little bit more about adjustable speed drives. So first of all, 4 subjects I want us to talk about here, and first one is motor efficiency. Then we'll talk about history of motor efficiency. What does the future hold, and some of the impacts that we need to consider when specifying a premium efficiency type motor. So first, what is motor efficiency? Efficiency is not to be confused with energy conservation. Energy efficiency may be achieved by keeping the net energy output of a system constant while reducing the energy input, versus energy conservation refers to lowering the total energy input without necessarily keeping the energy output the same. A little bit of history here. This is a little dated, but over 30 million electric motors are sold each year for industrial purposes. There's over 300 million motors in use in industry and infrastructure today. All of these motors make up over 40% of the global electricity consumed, and this is in driving pumps, fans, and compressors, majority of the electric motor operations. Consequently, there's a focus on improved energy, obviously. And with the heightened concern over global warming, this has led to even higher efficiencies being demanded. Motors can have a 30 to 40 year service life, and the average motor consumes about 4 to 10 times its initial cost in electricity per year. So that's equivalent to a car costing over $100,000 to operate per year. To give you a little graph here, this is a 20-year life cycle, the cost to operate a motor over 20 years. You can see that the initial cost is minuscule compared to the total operating cost, which makes up over 90% of the cost in operating a motor over a 20-year lifespan. History of motor efficiency. Two industrial standards have led the way in an effort to protect the environment by increasing motor efficiencies. The two majors are the Electrotechnical Commission, IEC 60034, and the National Electric Motor Manufacturers Association, or NEMA. There's many others out there, but these two are probably the most common and well known. The National Electric Manufacturers Association first made a distinction between standard and energy efficiency motors with the 1990 revision of NEMA MG1, 1987. That would become the standard for the Energy Policy Act of 1992. Then in 1997, a provision of EPAC took effect that mandated efficiencies to be compliant with what was in NEMA Table 12.11. Now this incorporated 1 through 200 horsepowers, 2-pole, 4-pole, and 6-pole machines, basically general purpose TEFC and ODP type motors. Note that this did not cover all the motor horsepower ranges, nor did it cover all the horsepower, all the RPMs as well. C-face motors were not included, nor were closed coupled pumps or special purpose type motors. Then the Energy Independence and Security Act of 2007 became effective for motors produced after December of 2010. Now this change incorporated a lot of the motors that weren't originally included, and that was the design C motors, closed coupled pump, footless designs, vertical shaft motors, and 8-pole or 900 RPM motors were now incorporated. So you can see over time, they've expanded into larger horsepowers and incorporated more and more of the different types of motors that were mandated to meet these higher efficiencies. The United States follows basically the NEMA premium efficiency standards, whereas the rest of the world, most of the rest of the world, follows the European Union Directive 640, which is identical to the IEC standard 60034. And it is broken down into several categories, starting with IE1, which would be a standard efficiency, and then progressively the efficiencies values go up as we go through IE1, IE2, IE3, IE4, onto the future of IE5 and IE6. The majority of the world does follow the IEC standard. To give you a little graph here, kind of shows where the efficiency values have gone. You can see the standard efficiency, EPAC was a little bit higher, then NEMA Premium is even higher still. To giving you an idea of the energy cost, we'll take an example here of a motor operating for 8,760 hours per year, which is basically a 24-hour operation. And we're going to assume a 12 cents per kilowatt. And this would be the cost to operate these motors under those conditions. If we look at the 200 horse with a standard EPAC efficiency value of 95, you see that the energy cost to operate that motor over that 1 year of time is $165,000. If we look at the NEMA Premium that had a 96.2% efficiency, the cost to operate that motor is $163,000. So the savings per year to operate a premium versus a EPAC efficiency is over $2,000. So you can see the payback comes back rather quickly with that slight improved efficiency. This here kind of gives you an example of what's going on inside the motor in a premium versus an EPAC and a standard efficiency. If you look at the outside of the motor, you're really not going to be able to see a difference, but what goes on inside is the magic. You can see right away here that the premium efficiency motor has much more active material inside, much larger stator, much larger rotor. Also notice that the cooling fan on this TFC version is much smaller than what you'll find on the EPAC and the the EPAC and the standard efficiency. And that offers better efficiency because we have less windage with a smaller fan. So that's what's happening with the IE1, IE2, IE3 motors we see today, putting more and more inside the motor. Once we get into some of these larger efficiencies, there is a limit on how much efficiency we can get, so we have to come up with some of these newer technologies. So what does the future hold? Some of the technologies that are in effect today are die-cast copper rotors. These can be very expensive, but they do offer a better efficiency. Permanent magnet type motors, synchronous reluctance motors, and electrically commutated type motors. Future holds IE5 and IE6. Not too distant future, I predict those will be identified. Some of the impacts to consider with premium efficiency motor. Number one, efficiency cost savings takes into account only the motor efficiency. You must consider the system efficiency needs to be considered. For example, an increase in motor speed is typical with these higher efficiency design motors. 40% of all motor loads are fans and pumps that use power proportional to speed cubed. So therefore, an increase in speed of these premium efficiency motors equates to a higher load and vice versa. Also, you need to consider the physical dimensions may be different on some of these premium efficiency designs. Permanent magnet motors, for example, will be in a much smaller package given the same torque, horsepower, and RPM. As I said earlier, the full load RPM is typically higher on some of these asynchronous type motors. Also, PM motors, synchronous reluctance motors, and ECM type motors do require special drives. You cannot just operate these with a magnetic contactor starter. And also increased motor cost are another consideration for these premium efficiency designs. And with that, I'm going to turn this over to my co-worker Josh, and he's going to talk a little bit more about the adjustable speed drive portion of this.
Well, thanks, Glenn. I'm going to get into the advantages of using ASDs to achieve energy savings. So there's three main things I'm going to talk about today. First, I'm just going to review what drives do, how we would properly size them, depending on the application. And then we'll talk about different ways to achieve cost and energy savings when using an ASD. And then I'll finish up discussing our energy savings estimator software that we offer. So let's talk about applications first. So, just to start out, you're going to hear me say ASD, adjustable speed drive. We also refer to drives as, they have many names, basically. VFDs, You have variable frequency drives, VSDs, variable speed drives. Some people just say drives or inverter. They all really mean the same thing. We personally say adjustable speed drive, but you'll hear me use them interchangeably. It just depends on what I'm reading. But here's, we'll start out with a basic 3-line diagram of an adjustable speed drive. So what does it do exactly? So, what a VFD does, it basically takes your incoming 3-phase AC power, first hits a diode bridge rectifier section that converts that AC power to DC. It creates a DC ripple here. See the positive cycle, the negative cycle. Then there's a DC bus capacitor section that filters that DC ripple that we then invert back from DC back to a square sine wave output to our motor, right? Using our inverter section of the drive, which uses IGBT switching devices to create this square pulse sine wave, right? So just a little background on what a drive does, right? And how it achieves, sending the motor that voltage to create that torque that the motor is utilizing. So when we're, properly sizing a drive to an application, the first thing we as application engineer ask, what is our engineering variable, right? In this particular example, looks like it's a pump, right? This pump has an impeller, it's creating discharge, and the motor will then be connected to that impeller to utilize the motor's torque to create that discharge and suction, right? So, we have different applications that we use for our motors. They're creating the torque, but then we're going to use a drive to really give the motor the proper voltage and current that it needs to create that torque, right? So, there's 2 standard applications that we're looking at for the most part. Well, one being constant torque applications, second being variable torque applications. So I'm going to talk about each of these. So the first one, constant torque applications, right? You're mostly looking at conveyors, compressors, lifting equipment such as cranes and hoists. Then you have, extruders, things like that, right? They typically require 150% overload for a minute, and we would recommend a heavy-duty drive for these applications. What we're mostly going to talk about today, though, is variable torque applications and how they achieve energy savings. These are really your centrifugal fans and centrifugal pumps, right? They typically only require 120% overload for a minute and a normal duty drive. So, the way I tell people is if it's not a centrifugal pump or fan, it's usually constant torque, but today we're primarily going to be talking about our variable torque applications. So when we're properly sizing our drive, you want to select a drive based off of its full load amps, not the horsepower, right? You always want to double check the motor full load amps and the drive's full load amps and ensure that the drive's output current is greater than the motor's. Drives, so a lot of people ask, can we factor in the motor's service factor? We do not recommend that. We really just want to go off the nameplate full load amps of that motor. And the drive itself does have a built-in overload level as well, right? As I said in the slide before, on your heavy-duty applications, heavy-duty drives, you're looking at 150% overload for a minute, whereas your normal duty drive, you're looking at 120% for a minute. So let's look at this particular example. This is a 460-volt motor at 200 horsepower and 1,800 RPMs. Its nameplate full load amp rating is 232 amps. When we're sizing our drive, of course, you want to choose the same voltage, but really, you want to make sure that the amps of the drive are at greater than or equal to the amps of the motor, never less than. You can run into cases where maybe the drive is same horsepower but has a less full load amp. That's why we always say double check the amps, make sure it's drive output current greater than the motor full load amps, and you are good to go. So that was just a little background on drives and different applications. Now we'll get into the the important topic of today, which is what are the different ways that drives can achieve cost and energy savings, right? So there's really 5 main points I'm going to talk about today. The first being process control, right? When we're using a drive and an ASD, a VFD, we are able to vary the speed, right? Because that's what the main job of the drive is when we put it on a motor. Rather than continually running our motor at 60 hertz, our drive allows us to vary the speed from 0 to 60 in most cases. Some applications call for higher speeds, but being able to vary our speed means in certain applications we can vary our flow from 0 to 100%. And then we have process control algorithms built into the drive's microprocessors that I'll talk about that will allow us to achieve this. Secondly, the drive is basically a soft start built in, which eliminates your motor inrush current. This current's typically 6 to 7 times the motor full load amps, which essentially is a waste of energy. And power companies do not like that inrush, right? It could also be damaged to your electrical equipment. A drive will basically eliminate that. We'll talk about that in detail. This also leads to less mechanical stress on your equipment. Basically, it goes along with the next point, having an unlimited number of starts, you can essentially start and stop your drive as much as you want, which is softer than simply running your motor across the line, starting your equipment over and over can lead to mechanical stress. So overall, those two things really, achieve your cost savings overall, right? Cost and energy savings. And then finally, we will talk about when we're using variable torque applications, they follow what's called the affinity laws, which allows to achieve energy and power savings. Variable torque applications, again, like I talked about a few slides ago, are mostly our centrifugal pumps and fans. And because of that, I think Glenn briefly mentioned too, the square relationship and the cubic relationship between torque and speed and power, right? Using those laws, we can achieve our cost and energy savings. So let's talk about each of these 5 points in greater detail. First, varying the speed and flow, right? We have what's called process control, right? So the main process control algorithm that our drives would utilize, if you want to automatically maintain some variable, would be the proportional integral derivative control system, otherwise known as PID, right? A lot of cases, you may just be manually increasing and decreasing your drive and motor speed to achieve the goal for whatever your process is. But on a lot of these, fan and pump applications, you may just want to maintain some sort of variable. This particular example I show here is temperature, right? Perhaps our process is temperature, and we are trying to maintain a temperature of 75 degrees, for example. And, rather than having to constantly increase it and decrease it, we can have it automatically maintain a temperature by increasing and decreasing this fan, right? So the PID algorithm in the drive will do that, right? So in this particular example, we have our temperature. We have a sensor that is feeding a transducer. A transducer basically converts this temperature into an electrical signal that is then given feedback to our drive, which is trying to maintain a set point, maybe a hertz set point that is corresponding to some temperature, right? And then the drive will increase and decrease its output speed, which in turn is increasing and decreasing our motor and fan speed to maintain this set temperature. So PID basically does that for you. And here we'll see, obviously there is some programming involved in our drive to do that. In our drives, it's in the parameters of the F300s, right? This is just a control diagram showing that. And of course, you do need feedback to do that, right? The drive needs to know what the temperature is in order to try to maintain that temperature. And with us, it's usually 6 parameters you can set in our drive to achieve this PID. Again, PID is proportional integral derivative. Those are 3 different things you're looking at to change the system, right? Proportional means, it's looking at how quickly do you want it to change, right? Integral is how over time do you want it to change, whereas derivative is the state of change that you're looking at, right? Again, our drives has this programming built in. Really, you don't need to know all the math behind it. You just need to know what you're trying to maintain. And we do have many application notes as well to walk you through step by step on setting up PID. So again, that is one of the first ways we can achieve energy savings, right? By automatically increasing and decreasing our drive speed to maintain some variable, right? But automatically, again, being able to manually increase and decrease the drive speed will give us those advantages over not using a drive, right? So secondly and thirdly, we have basically the ability of the drive to eliminate motor inrush, leading to less mechanical stress on our equipment, which also means lower maintenance, right? So when you're using a drive on a motor, the starting mechanism is different than if you were to run your motor across the line, right? When a drive is used to accelerate the motor, your output frequency and voltage, they start off at 0 and they gradually increase, right? And that's the basic job of the drive, is to provide that voltage and frequency for that motor. And being able to accelerate eliminates your motor inrush, right? That motor inrush is really, when you're using a drive on the motor, your starting mechanism is different and you don't have that inrush, right? This leads to, less maintenance, right? Less mechanical stress than simply starting your motor across the line. So fourth, we have basically an unlimited number of starts when you're using a drive on a motor. So during a cross the line start, you'll see a lot of motor heat with that motor inrush that we just talked about. When the motor's inrush current is around 650%, the motor heating is about 6.5 or 42 times the heat produced when it's fully loaded, right? Just doing that over and over, right, you're going to decrease the life of your motor and your rotors, right? This can lead to rotor failure. But when you use that soft start that's built into the VFD, you can reduce the inrush and extend the amount of time the motor can draw that higher current. Most large motors are rated for 2 cold, 1 hot start. That's kind of a industry rule of thumb. That doesn't mean that's the only number of times they can start, but it means if you are starting a motor, you want to start twice. You can start twice in succession at room temperature. If not, you want to make sure you can start once at its operating temperature. But when you use a drive, your motor current will rarely exceed 100% because the drive has built-in protection, right? It has microprocessors built in. You can program it to trip under the nameplate current. If you want it to go over and test those overloads on the drive, you can do that as well. But basically, motor heating will, should not be an issue when you have that drive, as it will protect your motor and allow for those unlimited amount of starts without damage and rotor failure. So you're really extending the life of your motor and achieving those cost savings over time. So finally, the last way we can achieve our energy savings is using the variable torque affinity laws. So, I talked about variable torque loads earlier, right? We're looking at our centrifugal pumps, centrifuges, fans, blowers, right? This picture here is a large fan actually in our manufacturing warehouse, right? Just as an example. And when we look at variable torque loads, really the torque requirement increases as a square of the speed, and the power requirement increases as a cube of the speed, right? So remember these two as, you can see right here, energy savings are possible on these loads, right? Because of these affinity laws, right? Centrifugal pumps, not positive displacement pumps, right? Those are constant torque. Most all your fans and your centrifugal compressors, but not all compressors, right? So anything centrifugal, right? It follows these laws, right? So you see the main one we are concerned about today is this one, right? This cubic relationship between power and speed. What this cubic relationship gives us, it shows that a small change in speed leads to a large change in power, which is how we get our energy savings on these centrifugal variable torque loads. So, if we were to, this is a table, approximate, things are rounded up, but any use of a damper or valve for control can give us potential energy loss, right? Eliminating these and using the drive to do it can increase your process efficiency and reduce those operational costs. So if you look here at your table, just simply being able to decrease your speed by 20% on those variable torque loads can save you 50% in power, right? Which goes a long way. And if we look here, really we can calculate the dollar saved per year using a drive because of these affinity laws on our variable torque loads. So the first thing you would do is really, write down your application horsepower, convert it to kilowatts, and then you would, say, for example, I'm going to reduce it by 20%, right? And this gives me 50% power reduction, which I'd put here. I'm going to run 8 hours per day, 7 days per week, calculate how many that is, how many hours in a year I would be running, right? And then I just need my, kilowatt hour dollar rate. And then I'd multiply the kilowatt times the power reduction times the hours run per year times the kilowatt rate, and I could get the dollar saved per year, which a lot of cases will be more than what the drive's initial cost was. So what that means is the drive on these variable torque, pump and fan applications will essentially pay for itself, right? So that's where we see our biggest energy savings is just utilizing the drive to run, just by decreasing its speed a little bit can really save a lot of power, right? Just going from that 60 hertz to 55 or 50, right? And then if you utilize, PID and automatically do that, you could even stretch your savings there. And then overall, to go with our other 3 points, just simply having the drive by itself, eliminating the motor inrush, eliminating that energy loss and heat can really extend the life of your motor and all your mechanical equipment, lower your maintenance costs to add up to really a lot of energy and cost savings for your system. So just to run the motor, you really want to choose the correct volts per hertz pattern. Really it's a parameter on our drives that you would pick, a constant torque versus a variable torque load, right? You'd want to go in and make sure you program it correctly for that most efficient operation. You could see here, for example, a constant torque load, its volts per hertz pattern is more of a linear, whereas a variable torque load, you're going to see more of a curve, right? Kind of follows those affinity laws, right? And you're going to have your lower voltage at lower frequencies, right? So you always want to make sure you don't want to just, start your drive out of the box. You want to make sure you do your legwork, know what the application is, and properly program it for that, right? So I want to finish up and talk about our energy savings estimator software. Really, those calculations we just did 2 slides ago using the table and the, long formula, that's fine if you're maybe looking at one drive, but what if you're looking at putting at multiple drives on a system and you really want to see running it at certain duty cycles, what we'll get as a savings? Well, we offer a software at no charge on our website that can really look at that for you. It's called the Energy Savings Estimator, Toshiba Energy Savings Estimator, and it'll really help you reduce your energy consumption when driving a variable torque load, right? So really, there's 5 steps involved in the software. You enter in your information, enter in your utility, your electrical utility information. What's the price of your electricity? How much are you using? And then, step 3 is what I have screenshots of, is step 3 and step 4. Step 3 is where you're entering your system data, right? You have your type. Is it a fan application? What kind of flow control do you have right now? And then if you were to put a adjustable speed drive, what is the initial cost of that drive? How many do you have? And then you would, try to estimate your percent flow, right? It looks like this particular example, they're mostly running at 60%. And, how many days per week, per year? And do you get a, incentive, right? And then you go to the next step. You basically, it'll put out, this is what your system is using for energy in kilowatt hours. Here's your equipment cost. Here's what you have presently. And then if you were to put a drive, how much your carbon footprint would be reduced. And it actually spits out, the amount of carbon dioxide you're saving, the tons, right? And then your yearly energy savings in dollars, right? That's the big one, because then it can give you a estimated payback time. In this case, this one was about 0.28 years. That's like almost 3 months. And the next thing you can do is it will basically print out a report. And I personally have traveled with end users and customers and done this software with them, maybe if they didn't have drives and they were trying to learn about them like you are today, and see what they can do for a system and how much energy they could save. Really, just if you utilize this software, it can do it all for you. It can highlight your energy savings, how much your pollution is reduced, and really the payback time and return on investment time is really a big one for people. Just seeing that the drive will essentially pay for itself using its power savings, and it's nice to have all that data there. That is all I had today. That's all Glenn and I have today. So we want to thank you for your time and attention, and we appreciate you listening to us. And now we will be able to open it up for questions. Thank you.
Now it's time for the question and answer portion. Thanks very much for Glenn and Joshua's presentation, but please participate in the live Q&A with your Zoom invite details. These details can be found in the Additional Resources tab on the left side of your screen.